Thank you, George. Thank you, everyone, for coming. And I want to first thank the organizers for organizing a beautiful conference. I enjoyed it very much, and thank you for letting me speak here. I'm going to talk today about how do we find simple structures in complex astronomical datasets. This work was done in collaboration with Professor Brice Menard from Johns Hopkins University. And I always like to start with what I call the data landscape. You can see here, basically the x-axis represents the signal-to-noise ratio of the object or the signal you're looking for, and the y-axis represents the description length, such that as I go right in this diagram, I'm moving to signals which have lower and lower signal-to-noise ratio, and as I move upwards in this diagram, I'm looking at more and more complex objects. And the thing I'm trying to suggest is that usually in astronomy we're down there. We really like using Gaussians. We like second-order moments. We usually are able to describe rather simple things, but things like, I don't know, cats or the pillars of creation are things that are more difficult to describe, and we're not doing it well enough. Now, on the right part of this diagram, we have developed very robust statistical tools in order to really mine our data sets and basically extract these very weak signals. But the question is, what are we doing here? We have examples like cats and, as I said, the pillars of creation, but we have more complex examples as well, like maps or books. How do you define an object within a map? How do you start even describing this complex structure? And there are various ways of doing that. One way, you can use either neural network or other types of algorithms in order to describe a complex object. So I'm trying to build an algorithm that will describe an object. Another thing I can do is, instead of trying to describe each object in my sample, is to try and study the relations between different objects. So this is rather different. I'm looking at similarities between objects and how objects interact with each other, rather than trying to describe each object. And one such relation is a sequence. Now, when I'm saying a sequence, I mean a set of properties that change continuously as a function of some parameter. Now, I'm showing 3 examples of sequences as a function of time, because this is something that is very intuitive to us. So we have a one-dimensional case. These are supernova spectra as a function of time. And you can see that we have many, many features, many properties here, and they change continuously as a function of time. I have 2D example of a Spider-Man that is dancing. And again, we have some structure as a function of time. Humans are also a sequence. We're not 3-dimensional. We change, our volume changes, the way we look changes, but also the way we think, the way we talk, and it forms a continuous sequence as a function of time. So these are all things we're familiar with, but we also have sequences as a function of other parameters. And I would argue that in astronomy we have a lot of these. One of the famous sequences is the stellar sequence. So you can see here example of stellar spectra. They look extremely complicated when you see them for the first time. There is some continuum emission, lots of different lines. Some of them are narrow, some of them are broad. And basically, Kai, you asked yesterday, why do we call something an AGN or not? We started by calling these O-type, B-type, A-type, and this is something that we do when we do not have enough information to say this is the sequence. This is one reason. The second reason, I think, it's because we do not have powerful off-the-shelf tools to recover sequences. So basically here, the nice thing about this is that this entire complexity, something like 90% of the things that you're seeing here, can be described by a single parameter, the temperature. The sequence is driven by the temperature of the stars, and this is what the HR diagram represents. I only need the temperature to know almost everything I need to know about the stellar spectrum. Another example is the Hubble diagram. Here we're talking about the morphology of galaxies. And basically, in astronomy, we expect to find sequences rather than classes. And the reason for that is that we have some physical processes that are going on, and they will change the properties of the objects that we observe continuously. We expect to find sequences in metallicity, in mass, in luminosity, in cosmic age, in many various parameters. And basically our goal is to try and build an algorithm that will recover this sequence. So this is basically what Brice and I try to do. This algorithm is called the sequencer. And basically what it does, it takes a bunch of objects and it reorders them according to some detected sequence. So what you're seeing here is an input dataset. Each row here, you will see this box plots a lot. Basically each row in this diagram is an object which has various features. The features are just color-coded. So if it is flux, it is color-coded by high flux, low flux, white and black. And basically this is the input to the algorithm. This is the output. So what I did here, I took Einstein's picture and I shuffled the rows in the image. Okay? And these shuffled rows were the input to the algorithm. And the algorithm discovered that there is a clear sequence. Einstein's image is full of correlations. You can actually, it's a perfect sequence. And it reordered the objects according to the sequence. Now, this algorithm, first of all, there are several things that are important in it. First of all, it has no tuning parameters. And this is important because when I'm doing unsupervised tasks, any tuning parameter that I have and I can change the results. And if it changes the results, me as a scientist, I can change the different tuning parameters until I get to the conclusion I want to get to. So I do not want to have this option in my algorithms. So this is one thing which is very important. We can work on one-dimensional data sets like spectra or light curves, 2D like images, 3D, IFU cubes. You will see how we make it happen. And the most important thing that we have a score. We have a figure of merit. The algorithm not only returns to us a sequence, it returns a score, whether we found a sequence or not. Just like chi-square, I can use it to know if I had a good fit or not. This algorithm provides the same thing. So the way we're doing it, I can break it into two parts. The first part is assigning some sort of distance or proximity between the objects in my sample. Okay? These can be various types of distance measurements, but given that I have this distance between the objects in my sample, I can start to explore the structure in this metric space. Now, let's assume that I have a metric. I've chosen a metric. And basically what I have is a distance matrix that describes the distances between the objects in my sample. So a spectrum I and a spectrum J have a distance of Dij. Now, the easiest thing I can do to recover a sequence is just start with one object and ask who is its closest neighbor. Who is the closest object with the shortest distance within this matrix, and put it as the next object in the sequence. Then redo this process again and again until I used all the objects and I have a sequence. What's the problem with such an approach? You can see it here on the right in the spectra. So basically we are looking at quasar spectra. You can see that the sequence starts to form here and then there is a jump. The jump is due to intrinsic variations that the objects have. If the sequence is not perfect, if I have some other intrinsic things going on there, my sequence will be dominated by things like this. Basically, what I'm trying to say is that local optimization is not good. When I'm looking at local proximities in my distance matrix, I will not be able to extract a general structure. So the way we're doing that, a distance matrix can be described as a fully connected graph. Basically, every object in my sample, spectrum I, is connected to all the other spectra. The edges represent the distance that I've measured between the two objects. Now, imagine that this thing is a fully connected graph. I didn't want to make it too heavy on the edges, but imagine it is fully connected. And basically what we're looking for is a structure called minimum spanning tree. A minimum spanning tree is unique. So again, I have no choices. It's a unique structure given a fully connected graph. And it is a subset of the edges such that I have the minimum possible edge weight. So this is the minimum spanning tree of this graph. Okay? And the reason why we like this structure is because what we're doing here is a global optimization. I am looking at local connections because when I'm trying to minimize the sum of the edges, I want to keep the shortest edges in my graph, but what I'm doing is a global optimization. And this is why it allows us to actually find a sequence. Now, let's say that this is the minimum spanning tree that I got. Imagine that every time I have a branching, basically I have an object there. And when I'm plotting it like this, I hope it is intuitive that this axis is the sequence. Basically, I have some long axis within my tree. It defines me the sequence. And the axis that you're seeing here can be either scatter or some secondary sequence that we have in the data. Now, I can have various types of minimum spanning trees that I get. I can get something that looks like a ball, basically. It tells me that there is no sequence in the data set I've looked at using the distance matrix that I'm using because I cannot find any geometrical structure here. And we define this score, the axis ratio, basically the height of the tree divided by its width. So here we do not have a sequence. In comparison, here we have a clear axis on which the objects lie, and the axis ratio in this case is closer to 10. This is basically what we use as a score. And the cool thing about it is that it is purely geometrical. At this point, after I've constructed the minimum spanning tree and I'm looking at the geometry of the tree, it does not depend on the metric that I've used. I can use different metrics, I will get different trees, but this number will range from 1 to n, the number of objects in my sample. This allows me to compare different metrics. And this is extremely important because, as you all know, all the people that have tried to measure distances between complex objects, different metrics are sensitive to different types of information within our dataset. Not every type of metric is suitable to find a sequence or any other type of task we want to do. So basically, and another very important thing is that different metrics over different scales see different things. So if I'm looking at small scales on my data set or on large scales, I will see different things. So basically what we can do now is taking various metrics and applying them, measuring distances on different scales on the data, resulting in different minimum spanning trees with different axis ratios. We can aggregate all of this information into our final sequence with a final axis ratio. This is what allows the algorithm to choose the best metric and the best scale in which there is a sequencing relevant information. And this is how we get rid of the tuning parameters, basically. The algorithm, because it has this figure of merit, it can optimize and find the best solution according to the axis ratio. And as we know in many examples in machine learning, aggregating many estimators usually results in a better performance. And this is what we're seeing in most of our cases. Now, just a warm-up example. These are quasar spectra from the SDSS. These are in observed wavelength. And basically what you can see here, we're seeing the continuum emission and various narrow and broad emission lines. Okay? So I'm taking these objects, and these are the input to the algorithm. What you can see here on the left, again, it's this box plot I've shown you before. Every row represents a quasar spectrum, where black is low flux, yellow is high flux, and this is the input. The output is what you're seeing here. So you can see that the sequencer found the redshift sequence. Basically, emission lines move across this image, and they do that because of the redshift, basically. Now, this is not, scientifically, it's not an interesting example because we know that this is what redshift does. But I think in terms of algorithmics, this is the most important example that we have. First of all, because we can track, the algorithm can track how information moves from one feature to the next. Okay? Things are moving and the algorithm is able to find that. The second thing that is very important here is that these emission lines are less than 5% of the total flux of the spectrum. Most of the flux in the spectrum is the continuum. And most algorithms that we're used to working with will first of all focus on the element in your objects which have the largest mass or flux or magnitude. And here you can see that regardless of how small this feature is, if this feature drives a sequence, this is what we'll find. Okay? So what can we do with this tool? What type of science we could do now? I will try to make it rather fast. This is what we call the M-sigma relation. I hope you know it. We now know that in most massive galaxies we have supermassive black holes. And one of the most astonishing discoveries that was made that the mass of the supermassive black hole correlates with the stellar velocity dispersion in the galaxies. This may suggest that the galaxy and the supermassive black hole co-evolve in some way. So the supermassive black hole has some significant impact on its host galaxy. And the points that you're seeing here are all are galaxies in the local universe. They are close enough that we're able to resolve the gravitational potential of the black hole. We can see individual orbits of individual stars, and therefore we can have a direct estimation of the black hole mass in these systems. Okay? Now, if we want to study how M-sigma relation evolves as a function of cosmic time, we need to be able to go to systems which are farther away, in which we cannot resolve the gravitational potential of the black hole. And in that case, we're using AGN. Very simply, AGN are divided into two groups. This is what we call type 1 AGN, this is type 2, unobscured, obscured. When you're looking at the vicinity of the black hole, we have an accretion disk, and we have what we call the broadline region. These are clouds that are located in the vicinity of the black hole, and they are gravitationally bound to the black hole. Further away, we have clouds which we call the narrow line region. These are on galactic scales. The gravitational potential of the galaxy is what affects them, and they are photoionized by radiation that comes from the accretion disk. This entire thing has this dusty torus, and basically the inclination of the system with respect to the line of sight will determine which type of object will we see. So in type 1 AGN, unobscured, we see broad emission lines and the continuum that comes from the accretion disk. These broad emission lines are used to measure the black hole mass in an indirect way. So we can measure the broad lines, and from that estimate the black hole mass. However, since the accretion disk outshines the stars in the host galaxy, and therefore we do not see the stars. If we do not see the stars, we cannot measure the velocity dispersion. So in these systems, we can measure the black hole mass. We cannot measure the stellar velocity dispersion. When we go to obscured AGN type 2s, the accretion disk and the broadline region are obscured by this dusty torus. So we cannot see the accretion disk or the broad lines. We cannot measure black hole mass. But the galaxy is observed. We can measure the stellar velocity dispersion. This is basically where we're at. In one system, we can measure black hole mass, but not the stars. In the other system, we can measure the stars, but not the black hole mass. Please notice that the narrow emission lines, we see them in both types of systems. Now, people have been trying to do M-sigma relations with AGN. It is much more difficult, but it is possible. There aren't many systems in which this was done, and there are various ways of doing it. One way is if the galaxy is close enough and it is resolved, we can take a spectrum here, and this will be a type 1 AGN. From the broad lines, we will estimate the black hole mass, and if we'll go further enough, if the PSF obviously allows us and the system is close enough, we will be able to measure the stellar velocity dispersion. But again, this is not something we can do at redshift of 2, of redshift of 4, of redshift of 6. And we want to be able to do things like this. And here comes the sequencer. So we have sequenced type 1 AGN, unobscured AGN from the Sloan Digital Sky Survey. This is the ordered spectra. It is rather difficult to see what is going on here, but the sequence is mostly dominated by the width of the broad lines. Not only by the width, but by their shape. And we will see it later on. If you take this sequence now and you stack according to the sequence index to get median spectra, this is what it looks like. So we have some continuous change both in broad lines and narrow lines at the same time. Okay? This behavior allows us to find a new correlation between the narrow line region and the broad line region properties. Okay? This is what the sequencer allowed us to do that we weren't able to do before. Now, finding a correlation between these very different gas clouds that sit on very different scales is important. If we want to understand AGN physics, this is important to understand how come this diversity of properties that we're seeing in the narrow line region, which are on galactic scales, and broad line regions, which are in the vicinity of the black hole, how do they know about each other? So this is one interesting aspect. The second interesting aspect that we can use this correlation to estimate the black hole mass in type 2 AGN, in obscured systems. In type 2 AGN, I'm seeing the narrow lines. Using this new correlation, I can estimate what is the width of the broad lines, and from that, I can estimate the black hole mass. So using this new scaling relation, we're able to measure both the black hole mass and the galaxy properties for thousands of systems. And this is basically what you're seeing here. So all the empty points are the type 1 AGN I've shown you before. The orange points, it's rather difficult to see, but we have measured it for 10,000 type 2 AGN. And you can see that the M sigma relation that we get and the M sigma relation that people find in type 1 AGN are roughly consistent. Not only that, the scatter around the best fitting M sigma relation is roughly the same for type 1 AGN and type 2 AGN. So this is the type of science we can now do because of the sequencer. And what have I learned from this example? So these spectra I worked with are public for many, many years. And there were numerous works trying to measure these lines, the broad and the narrow lines. We have the SNR, and we only need roughly 300 spectra to recover this correlation. So how come we didn't find it before? And I think my lesson is that it's not about the size of the data, it's about its complexity. People up until now, you can see the complexity of these various broad lines. You can see this tiny peak up here. This comes from a narrow line. But you cannot know whether this narrow line is that strong or that strong if you just decompose them to many, many Gaussians. So I think this exercise showed me that we are not limited by the data, but by how we extract the information from the data. And if I come back to the data landscape, if you give me enough Gaussians, I will be able to fit a cat. I will be able to fit anything you will want. The question is whether I can use these Gaussians to understand something new about cats, whether I can find relations between different types of cats using these numerous Gaussians. And this is why I think we need the sequencer to be able to go to this regime and look for complex trends, simple trends in complex datasets. In the very near future, we will submit one paper about the sequencer and another about the M sigma and the black hole mass estimation. I promise that it will happen in the near future. We will have a web interface where you can upload a data set that you have, and the sequencer will run on it, and we will return the data set to you. If you want to admire my absolutely horrible coding skills, we will have a Python code available as well. That's it. Thank you very much.